Okay, we're going to conclude this little set of lectures with some thoughts on design of experiments that involve several factors. One thing that you want to keep in mind with the design of experiments, I've already mentioned, is that if you're looking at trying to model y as a function of x with one variable, then you don't want to have all of your data clustered around a very small value of x with nothing in between for a long time, and then at some large value of x you have a bunch more data. Putting a line through that is not a very sensible thing to do. This also, when you go to multivariable situations, is sort of a common sense area, but common sense is important. So let's go ahead and talk about what happens what can go wrong when you poorly design an experiment first. Okay, so we have a response variable, and we have these factors xk that can all affect variable y. And we refer to the levels at which we ran experiments, for example, on the relationship between these two things as the different values of the factors xk that were tested in the experiment, right? So we have low values and high values, for example. And a bad example of a poorly designed experiment, I guess I should say, is that if you're looking at the dependence of a reactor's yield on the reaction time and the reaction temperature, that's x1 and x2, then we could try and analyze these two variables one at a time, right? So we pick a temperature and we vary the time. And we go through and we see this sort of trend that it goes through a maximum, and we say, okay, now I'm going to pick the time that gave me the maximum yield, and I'm going to look at what was the effect of temperature, right? So now I have a constant time, and I'm varying the temperature, and again, I now see a peak, and I pick out this point, and maybe you would think, okay, that now I understand the nature of the response surface, and that is to say that I know how y depends on x1, x2, but really we don't, right? So if you think about the possible situations that could explain that data, there are many, right? So if I did a full two-dimensional plot of variable y as a function of, in this case, time and temperature, these lines, these curves, represent surfaces of constant y, and so the maximum in y might be sitting right here. And what we did was, in one experiment, we probed this. We chose a temperature and we varied the time, and that identified for us this point. And then in the second experiment, we chose the time and we varied the temperature, and that identified for us this point. And you can see we may still be quite far from the optimal temperature in this case. So for things like optimization, thinking about how to design your experiment can be quite important. Okay, so the ideal way to design your experiment is called the factorial design. If we have interest in multiple levels of a variable x, then we do all combinations of low and high values for variables x1 and x2, right? So here's the basic design. I have factors x1 and x2 that both influence some variable y, and I'm going to run one experiment with low x1 and low x2, experiment with low x1 and high x2, and now I have to run the experiments with high x1. Those are high x1 and low x2, high x1 and high x2. Okay, so pretty intuitive that if I think about a two-dimensional space here in x1 versus x2, that is the plane, the horizontal plane down here in the bottom of the figure, that in order to really get a good representation of how y depends on these variables, I need at least 4 points to say something about that, right? So you can see in this particular example that there's an interaction between x1 and x2 in the response of y, right? So if I tried to put a plane through these 4 data points, it just wouldn't fit through those, right? So we need to include in our regression model an interaction term between these two guys. So what is the effect of that interaction term? Let's try and see it in a different way. If we considered y as a function of x1 and x2, we can consider a model without these interactions. And then what we would see is that the regression model would force us to have the same effect of x1 at both high and low values of x2, right? So the regression model would predict this, when in reality the the data looks more like this, that when I have a low value of x2, there's a smaller value of x1, and when I have a higher value of x2, the effect of x1 becomes stronger, right? So this is a nonlinearity in our response, and it requires that we include terms that look like this, right? So we have this interaction between variables x1 and x2. Okay, so we can think about trying to isolate different terms from these very simple experiments where now we're thinking that we don't really have an excess of data to really go through and do a regression model. Let's just imagine that we have a designed experiment that is going to tell us about effects of these things from the values that we got. The one set of values that we got are what we have to go with. Okay, so here is the effect, the coefficient for the response of y to a change in variable x sub k, right? So in order to estimate that coefficient, you want to look at the average of the y values when k took the high value and the average of the y values when k took its low value, right? So it's the difference between these averages that isolates the average effect of a change in variable xk. So now you can go through and you can solve for this coefficient in your model by dividing this difference by delta xk. Okay, so if you prefer, you can imagine that y was actually a function of xk, and then what you would do is make a Taylor expansion and truncate that at first order. So that would give you y as y evaluated at the average position for xk minus some difference minus y evaluated at the average position for xk plus some difference divided by the difference in the xk variable. Okay, so these two equations basically are saying the same thing, right? They are finite difference approximations for the response of y to a change in this variable x sub k. All right, so if there are other variables, then we might average over them, and for the interaction effects now, we're going to need all four terms, right? So if we're interested in these interaction effects, those are a bit more complicated, and we'll need four terms to account for them. We can get that again from the Taylor series. We'll guide our construction of what terms will go into that interaction. So now I'm going to take the second derivative of y, and I'm going to vary both xi and xj to try and get an estimate for the strength of the interaction between variables xi and xj. Right? So I first take my derivative with respect to xi, and that now is going to be, well, actually, first what I've done is taken a finite difference to represent the derivative with respect to xj. So I've now got y at xi, and here is the average of xi plus, so this is the high value of xj, and then I've got the actual value of xi, and the other input is the low value for variable xj, and I divide by the difference in the values for xj. And now we have to go through and divide differentiate what's left in this curly brackets here by the xi component, and you see now that I have to multiply the difference in xi with the difference in the xj, so that's the xi high minus xi low multiplied by xj high minus xj low, and these are all the values that go in to estimating that coefficient, which would be beta 3 in the model above. Let me run back up here. So it's this coefficient would then be estimated by evaluating this derivative here, right? So this derivative is an estimate of that coefficient, and in order to estimate that derivative, I need to know something about the value of y at the high value for I and at the high value for xj. I need to know something about the value of y at the high value for I and the low value for xj. Here's low I and low j, and low I with high j, right? So we have 4 data points, and that's the key point here, is that it takes 4 data points to tell something about the interaction between these two variables. And so, if you were to try and do this with 3 factors, you can see that the factorial design is starting to get pretty expensive. I now have to run 8 experiments. I have, this layout with low values of x1, high values of x1, and then the reason we need 8, of course, is because we have 2 to the 3 different conditions, right? So This quickly gets quite expensive. There are partial factorial designs and other more exotic designs that will try to cut down on the number of data points that you need. And your book talks about some of those. But I think that's all we're going to do on design of experiments. Your book also introduces some notations here and some things called contrasts. But we're gonna go ahead and stop there and call that it for the design of experiments. And next time we'll do stochastic processes.